right, good afternoon, folks. Welcome. Thanks for coming. I think we're a few minutes after 1:20, so we'll get started. My name is Mark Blaser. I taught at Shasta College in Northern California for a long time, about 26 years. And I have partnered with Carnegie Mellon University on some stuff we're going to be talking about here today. And a couple of years ago, I retired from full-time teaching, but kept my hand in on chem education research. And so I'm currently a domain fellow in chemistry in the Open Learning Initiative at Carnegie Mellon University.
I am Dhaval Doshi. I teach at Mount San Antonio College. It's located a little bit south of here, LA County, within the city of Mellon. I'm a full-time chemistry teacher, teach general organic biochem and general lab.
Okay, so unlike normal talks that I've given recently, I don't have 20 minutes or we have an hour. We tried not to just fill the hour with stuff to tell you. We'll see how well we did with that. But we welcome your interaction, your questions kind of throughout. So we're going to talk just a little bit about our origin story. Dhaval is going to be our first one instructor's approach and results. The system we use collects lots and lots of data on how students interact with the learning materials. And so we're going to take a look at what we can learn from learning about how students engage with the courseware, a little bit on math and learning chemistry, another instructor's approach and results. And we just selected a few. We've got a lot, but we picked the ones that I think are pretty well representative. And then we think that real chem can be a catalyst for chem education research. So maybe we're actual chemistry people here. We should talk afterwards. And then I don't know if we'll have time to do a little more with learning curves or not. We'll see. Not common. Okay, so maybe preaching to the choir here, may not, but there's a lot of evidence around that active learning methods are beneficial to students, but traditional lecture still dominates in STEM. Chemistry is particularly not the greatest at that. Active learning pedagogy can be particularly beneficial to underrepresented students. Underrepresented students that make it through the first semester of general chemistry, even just squeak by, can enter this sort of hyper persistent zone where they continue in their STEM. If we have increased structure, that can be really beneficial to students, and learning good, effective learning strategies or study strategies can help as well. And so Herb Simon, the Simon Initiative at Carnegie Mellon, named after him, a Nobel Prize winner in economics, I would say a polymath. Is that pretty fair to say? And I believe started the computer science program at Carnegie Mellon University. I do like this quote: improvement in post-secondary education will require converting teaching from a solo sport to a community-based activity. That was talked about in some of the panel discussions today. We got to work together on things. And at the Open Learning Initiative, courses are developed incorporating learning science and expertise from the people in the domain. Heavily uses instructional technology and instructional design. There's a lot of software development involved. We check on how the user experience is, universal design, and it's a lot of project management. So there's a big team of people working. Joe may have a better idea of what the total number of people in our project now.
21, 22.
And I think it's actually probably more if you like do have partial roles, but it's more than just being doubled by a long shot. And the science of learning, course design, how students perform on things, what the instructors do in class, all funnels in some data, and all of that stuff is sort of taken into account in trying to design a better learning experience for students and do research on what's working and what isn't. So in 2020, we went and got a grant from the Learning Lab. That's why we're here. Because of this sort of problem in general chemistry, we wanted to implement some engaging interactive courseware that has a lot of research behind it. We wanted to build a community of practice, which we did. We wanted to collect materials from instructors and then iteratively improve the courseware. We'll show you a little bit of how that works. And then use student data to figure out how better to couple what the students do online in the courseware and what we do in class. And we also, of course, want to make the courseware more equitable, more inclusive, more relevant, and more engaging. So we got this is the disrobed part of the presentation. We got a grant titled Improving Learning Outcomes for all general chemistry students through adaptive hybrid courses. It eventually, Sandy Razor, I think, came up with this, called it the AHA project for active, hybrid, and adaptive. We had t-shirts with and everything. And then our project timeline was, we were awarded the grant in March of 2020. The project officially started in July. We had a year.
Happening between March and July?
I thought we said no comments from the audience. Did we not make that clear at the beginning? And then we're going to collect baseline data in year one, collect data with a partial implementation and begin improving in year two, and then full implementation. And as Norm so astutely noticed, something did happen literally like 2 days, 3 days after we were awarded the grant. We were all fully online. So we changed our plans quite a bit. And the short version of it is pretty much everybody's online, including labs. We couldn't collect baseline data, and we had to scramble to improve the courseware, to build some online virtual labs, things like that. So, I mean, instructors, just give me something that we can pretend we're teaching somehow. So that ran from 2020 through 2023. Eventually we had 11 institutions, almost 30 instructors involved, and about 7,500 students. We'll talk about the courseware in a bit. It collects lots of data. We were getting 1 to 2 million student interaction transactions per semester. And we had a nice little team. I was hoping Marco would be here, and he's not. So we had Marco and Krishna and James and Saheba and Dave and Julia and Iliad and Wendy, sorry, and quite a few other people. And I think part of our story is that led to eventually Carnegie Mellon and ASU partnered, got a grant from the Gates Foundation to essentially continue the work we were doing. And it became, instead of Open Learning Initiative or OLI, general chemistry, it became real. And I think, yeah, we can do a little quick, what the heck does real chem look like? And ask questions if you got any. Sorry, this is a little awkward. We have to go to, oh, that's right, I got to switch. No. There we go. Okay, so this is an interactive online textbook and homework system with lots of bells and whistles. It has let's start with this. It has a sort of Netflixy interface where you have a unit. Those are like chapters, and then modules, which are like sections within a chapter. And you can schedule things, students can take notes, there are exploration activities, practice. I won't go into detail in all of these things. Students get some indication of their progress. This is me being a student in our demo course, which is apparently not for students. And I'm being a terrible student. I've only got 6% done, even though we're halfway through the semester. But it gives students like, what do you need to do, by when, what are the activities, and I'm way behind. And then in general, you go into let's say module, I'm picking electromagnetic energy and the Bohr model. And I signed in like just before the class started. Or just before the clock started. And, you want to start talking about yours while I log in?
Sure, yeah.
Um,
So want
So,
me to drag it back over so you can see it on.
Oh, that would
on
help,
this?
yeah.
Or that help?
okay, so meanwhile, I'll kind of, my end was I met Mark at a conference, and at the time I was thinking about adopting a flipped classroom model. Lots of literature up until then had said, flipped classroom model leads to higher student success, a better performance on standardized exams and so forth. And I was exploring at that time resources that I could use for the at-home pre-class preparation for students. So videos, interactive, substantively interactive activities and demos and so forth. And conversation with Mark introduced me to the OLI platform. Now it's called RealChem, but I'll be using those terms interchangeably. It's a different iteration essentially. And OLI had all those in one. It was a one-stop shop that had all of those. So Mark, do you want to kind of continue on and then I can take over?
Yeah, so thank you very much for helping with that. So, okay, so this is just a page. Anybody who's interested, we can give you a link to a course and you can explore and all that kind of thing. In general, there's some explanation, like a standard textbook. We include animations where they're useful. You'll note there's not tons and tons of text before. So here, there's a little bit of explanation about waves. There's one worked example. And then pretty quickly you get to either learn by doings, which are pretty much what they sound like. And so a student can, let's see, longest wavelength, they could pick the wave they think has the longest wavelength. They get immediate feedback if they're correct or not correct. Gives them some feedback also about why it's correct or incorrect. They can get something wrong and they get feedback that doesn't necessarily give away the answer, but may help them. You can ask for a hint. And everything that the student does is collected by the system. There's all kinds of different questions. You can enter numerical answers. You can have drop downs. You can have multiple choice. Oh, this is gonna. I won't try to. Just trust me. You can enter an answer and you get the same kind of feedback. You can also get hints that are helpful to you. And sometimes there's a number of hints that'll scaffold your way to that. Because students learn by getting good feedback on things. And anyhow, that's the basic idea. At the end of each module, there's what we call a checkpoint, which are, you can think of as homework, you can think of as formative assessment, you can think of as summative assessment, and then we have checkpoints at the end. And then there's a lot of other features. Dhaval will talk about some of them and how he uses them in his practice. And we won't get to all of them, so ask questions as needed. Try to get you to your slide. So. Oh, and yeah, we should probably say, what does RealChem stand for? It's for relevant, equitable, active learning chemistry and Dhaval.
Okay, so which teaching approach do you mostly use for now in your classrooms? I'm assuming everybody in here, or most people are chemistry instructors.
Yeah, who is a chemistry instructor here? Okay,
So do we use a sort of a traditional lecture, interactive lecture? As in a little bit of lecturing, some activities, 3 of those?
Mixture, yeah.
Mixture, okay, yeah. So I was kind of, somewhere along the lines as well, mixture, and as I said earlier, I was looking for flipping the classroom and looking for resources to best prepare students for I wanted to adopt more in-class active learning principle-based activities and a resource outside of class that the students can use to be better prepared for the in-class activities. And as I was introduced to OLI, now RealChem, it provided me with an opportunity to adopt the inverted teaching or flipped classroom model. This high level of engagement and substantive interaction that was built into RealChem that the students could participate in, and it wasn't just static, as Mark kind of showed, it wasn't just static reading or just solve this one problem kind of a thing. It was highly engaging for students and interactive. It gave them substantive feedback as well. There was videos, demos, everything in one place. So I thought that was the best tool, and I went ahead and started using it as for my students to prepare to pre-lecture preparation. So they came to the classroom with a baseline of knowledge, regardless of what their backgrounds were, what their previous chemistry knowledge might have been, and so on. Having interacted with real chem, they came, if they did the work, they came in with the baseline knowledge, and they were now ready for the in-class active learning-based principal activities. And I'll talk about this a little bit later. It gave the instructor on my end large amounts of data to interact and adapt on my end, my instructional practices, my pedagogical approach as well. Several features that I use as an instructor, I'll mention a few of them in the interest of time. One feature is there's a built-in discussion board along the lines of Perusal or Piazza. The great thing about that is built into the platform. So the students, earlier I had them kind of participate in discussions on Canvas. So they had to leave whatever platform they were interacting with and make a comment on Canvas. And that was another barrier in their way. But now I post announcements on there, I prompt discussions, I start discussions. As students are interacting with these activities on their own time, sometimes it's 2 in the morning, whatever their schedules may be. As they run into a question, they post a question on the discussion board itself. I answer it, or sometimes other students answer the question, so it becomes this online virtual discussion and also plays the role of virtual office hours. So that's one of the features. The other features is a high level of support is given to the instructor. So one form is these PET activities, highly structured, highly engaged activities, very dynamic. Not only sort of solve this problem, which is kind of a typical end of the chapter problem, happens to be in a traditional textbook. These are much more interactive, much more sort of molecular level representations and animations and so forth. So a much more dynamic experience for the students as they kind of engage with the material. These can be used in a group context or in an individual context. I've used these in engaging students in a whole class discussion as well. With an activity, they'll prompt me to do something. I'll interact with the PET activity, and they'll see how the pressure changes if I change the volume, for example, and so forth. Also, problem-solving activities are also given with the feedback suggested along with equity prompts. So you're not only focusing on the curriculum part of it, the chemistry, but you also give some attention to the equity and equitable practices of teaching a particular topic and so forth as you're teaching the topic. So here, these activities I have been very helpful for me because I can focus as a community college instructor. I need to focus on my students' problem-solving skills as they move forward to other chemistry courses. But at the same time, I just don't want them to kind of fall into this trap of pattern recognition and apply to a different problem, recognize the pattern, apply to a different problem, and so on. These are much more dynamic than that. So molecular representations, they answer, they get substantive feedback, detailed targeted feedback. So in my experience, it elicits not only sort of builds the problem-solving skills, but elicits critical thinking sort of responses from the students simultaneously. A lot of the activities are highly contextualized, real-world examples, how a scientist preparing solutions in a lab might kind of think about these things, diluting a particular solution. So it's not just, again, solve this problem, apply some pattern you recognize. It's contextualized, it's the real-world examples. I've used these as guided problem-solving activities to answer student questions, address student concerns as well. Also, there's high level of sort of interactive demos, videos, etc. So if a student has a question on titration, for example, I don't have to rely on now going to PowerPoint. Within the platform itself, there are these demos that I can address the question of titration. I can ask them questions about how to read a burette, for example, and so on. Everything is built within the platform. That's the best feature for me. I don't have to rely on separate PowerPoint or Canvas discussions and so on. It's the one-stop shop, as I mentioned earlier. There's these extra practice activities available as well, and these have been informed by data. So what we did was we looked at the summative assessments that are built into the platform, and the results of the assessments and the lower scoring questions, we have built more practice for the students. So as the students self-assess their own knowledge, sort of think about it metacognitively, how they are performing on a particular assessment and so on. If they feel like they need more help on a particular assessment question that they scored low on, these activities are available ungraded, but it provides extra, again, contextualized, with feedback built in and highly interactive activities they can practice. As an instructor, RealChem also provides me with a lot of data. So the data is provided at the class level, on the unit level, which are essentially chapters, or module levels, which are essentially sections within those chapters, and also provides data on an individual student level. So here I can see on a particular unit or module how the class is progressing. And I can see this for an individual student as well. And if I see a precipitous drop off for a student, that raises a red flag for me. I can contact the student, hey, what's going on? Or contact my supplemental instructor and tell them to kind of talk to the student and so on. So I can identify patterns of engagement using the data that's available through RealChem. Again, this is for the entire class, but similar data is available for individual students as well. Not only for the individual students, learning objective level progress and assessment responses are also available. So on a particular learning objective here, stoichiometric relationships, data is available that the students are doing okay. But again, this can be identified. So if on a particular learning objective, for example, if the data on the platform tells me that the student progress or assessment responses are low, now I identify that as somehow that topic didn't get communicated as it should have been. I can supplement my in-class discussion. I maybe need to have another discussion or have another activity that sort of addresses that particular topic.
Do you pull data across quarters to create like a global pool?
So I've focused on 1 or 2 semesters, but I am in the process of across semesters, sort of assessing the data and kind of seeing some patterns and that have emerged and so on. So for example, one pattern that has emerged is in the fall semester, incoming freshmen tend to take the Gen Chem 1 class. So the performance tends to be lower. In the spring semester, they've had a semester of college under their belt. Their time management skills and so on are slightly better, tends to be better data. So some general themes are emerging, but I don't have presentable data quite yet. I'm still looking at it. So again, these approaches, so again, my sort of approach as an instructor is I can use the data to adapt my instruction and my pedagogical approach in the classroom. So the platform is adaptive to the students. It gives them adaptive feedback on their learning journey. But on my instructional journey, it also gives me a chance and opportunities to adapt my learning based on the data that I collect. And as I've both on the student and on the instructor end, as the changes and adaptations have been made, there is data to support that students in general have achieved more success. So this is the academic year 2018-19. So before I started using OLI, the red line there is a pandemic, as we know. For the, and as we, so 2021, the middle is when we're completely online. So I'm not sure how reliable that data is because we have this excuse withdrawal sort of option. So 100% retention is maybe not reliable, but once we come back fully face-to-face, 21, 22, now we can make an apples to apples comparison between the rightmost column and the column that were there before, the middle being the pandemic years or year. So as you see, the bottom bars show that retention went up by 14%. So more students were persisting with the course. And there's a lot of data that shows that students persist with a highly structured course. They get into, as Mark mentioned, this hyper persistence zone where that persistence carries over to organic chemistry later on, and they tend to have more success in organic chemistry and so on. So more students were taking the class. However, if you see the top bar, they were succeeding by a 15% higher rate as well. So not only more students were remaining in the class, the withdrawal rates dropped, but the success rate, more students were passing those courses as well. That similar success is reflected in ACS scores as well. So again, this was before OLI, real-time adoption in the classroom. And we have done, my class and Mount SAC in general, the department has done better than national norms in terms of the mean here. But as we sort of come fully back to face-to-face instruction, fall 21, spring 22, the mean, as you may notice, doesn't change significantly. But the very bottom row, the persistence rate, the success rate, so your success rate as in students with a passing grade, A, B, or C, the success rate increases significantly. So I think the fall 21 drop is due to coming back the first semester after COVID, might be some artifact of online instruction. But if you go to spring 22, spring 23, the success rate has increased. So more students are staying in the class. And this is a standardized final exam administered by ACS that we give. And on the final exam, more students are taking the final exam. However, the mean remains the same. So more students are passing the course. By the way, spring 23, Mount SAC assessed the ACX exam as a department-wide final examination. So all 15 sections of Gen Chem 1 took the exam. There, the department-wide mean was 36.4 out of 70. And mine was 46, and indeed my section was one of the higher scoring sections for the department-wide assessment. And I think Real Chem OLI contributed significantly to that. Sort of this instructor effect was taken away. It was the system that was contributing to that higher levels of success. Similarly, as we sort of may have already know, the more they engage, higher ACS scores. Also, higher summative assessment scores lead to higher ACS scores as well. So the more they're engaging with the formative, learn by doing, did I get this, and the summative module and unit checkpoints, their ACS scores, there's a correlation that's seen. Similar success was also observed when a department-wide SLO was administered. So the SLO, the topic was solution stoichiometry. So it started with fairly sort of straightforward questions, define what molarity is. And then it kind of went into sort of dilution problems, straightforward stoichiometry problems, and some of the later on problems were limiting reactant, how much of an excess reactant, ionic concentration of excess reactants, and so forth. As you see, the red bars are my section and the blue bars are the department-wide data. As the sort of the problems grew in difficulty level, scores decreased, which was to be expected. But even for the more difficult problems, the students in my section performed significantly better than the department-wide. And this was administered while we were online during COVID, so there may be some sort of, cheating may be going on and so on, but the data still reflects that the students are still performing really well on even the more difficult questions. They're performing at a higher level than the department-wide data. The students seem to really like the platform. They like the high level of interactivity, the detailed feedback, the multiple opportunities to learn from the feedback. They like the dynamic activities, the videos, and so on. So the platform, the great thing from a student's perspective is not static like a textbook would be or solve problems. It gives them opportunities for substantive engagement, and it's dynamic. They can engage with it at different levels and different ways. And I'll pass it back. Yeah, go ahead, Simon.
For the bar graph,
Yeah.
how much of that is your excellence as an instructor versus the courseware itself?
I honestly think it's the courseware in the system because the ACS reflects better on that. Because I mean, I was the same instructor doing traditional lectures here, but the mean wasn't the same, but a lot of my students were dropping and they were not persisting with the course. So the mean is kind of skewed in the way because only the higher performing students remain in the class. But if you see spring 23, very few students dropped. So even the lower performing students were in class, but the mean remained the same. So I attributed that to the system, to be honest. And because I use the flipped classroom, so my role as a didactic lecturer kind of is minimized in that sense. Right, do you want to-
Sure, yeah. And just to jump on that, we're showing Dhaval's data, for a number of reasons, including they have ACS scores for comparison, they have SLOs, some things we can't get from all of our partners who have done this. Surely some of this is because Dhaval's a really good teacher. And we can't completely disentangle what's the OLI usage from what, is the instructor effect. But I think the point I want to make is all of these things we have from other instructors at other institutions, very similar type of results. Strong correlation between how much work you do on OLI and how well you do on whatever the assessments are, strong correlation, or at least, pretty good correlation between the higher stakes, the summative assessments in OLI and external ones, et cetera, et cetera. Same thing with retention and so on.
If I may, sorry, Mark, interject. We have very similar data from an instructor who teaches Gen Chem 2 at Cal State LA. there the correlation's even stronger than my class, so it may be maybe not me, the system is kind of doing the. Sorry, there was another question.
I have two questions, actually. One is, what is the role of group work or collaborative work either in or out of the courseware?
Mark, do you want to address or?
I will just say, in general, it varies widely by instructor. So we have, I think we're up to what, 45 instructors, Joe, Dorn, is that right? This
Oh.
fall, is that right?
Yeah, sounds about.
In the mid-40s, okay. And I know for sure, some of them do fairly traditional lectures, some do interactive lectures with little bits of group work. Some like Dhaval are very much flipped and quite a bit of group work.
And
So
of
it
course-
varies a lot, but
But the courseware itself is
Oh.
not related to any of the collaborative.
I would
It
say
is.
courseware facilitates whatever approach you want.
One of the things that we've worked hard at is adding these sets of activities for faculty to use that are tied to learning outcomes in the course, and that, can allow faculty to look at the data and say, all right, students need help with. I'm terrible in chemistry and I shouldn't be the one to determining molarity. And so, we're going to jump over to the molarity learning outcome, and here's some activities you can do in class, some of which can be done in small groups. And so we give them a script for how to do this in small groups. But we know that some faculty are taking that and delivering it as a lecture, and others are handing it out as individual. So we don't have quite as much control for what's happening as a collaborative set of activities. I think we aspired, when writing the real chem proposal, to bake into the courseware more opportunity for collaborative and small group work. Our eyes were bigger than our stomachs, as my mother used to say. And so while those collaborative style activities are still on the roadmap, we haven't gotten there yet with the platform.
My other question is just when you, when you have shared the results, what is the reaction from the entire department?
So we have pushed for department-wide adoption at Mount SAC for real chem, and the responses are really well, and I hope nobody minds me sharing, but there's a grant funded for a collaborative grant to adopt real chem with sort of mastery grading approach, and it's a collaboration between UC Riverside and Mount SAC. So more and more faculty are coming on board. My experience has been, maybe I'm not a good salesperson, but I work much better on an individual one-on-one sort of, hey, I'm excited about this platform, coming to my office, I can show you all the cool features. And so I have 4 or 5 faculty members from Mount SAC are using it currently for Gen Chem 1 and Gen Chem 2. But department-wide adoption is down the road, but yeah, they're excited. On an individual basis, when I try to present it on a department-wide basis, there's some resistance.
Yeah, maybe piggyback on a couple of these things. One, Dhaval just mentioned this grant, and it's an NSF HSI IU's grant that UC Riverside got, basically because of the Learning Lab grant and the work we did here, and then Real Chem, and so it's piggybacking. And so we want to make that distinct point. We also got a grant for GOB chemistry, an NSF grant, to essentially make a Real Chem OLI chem version of GOB chemistry, and we would not have gotten that without the Learning Lab and the Real Chem. The other thing is, I think Dhaval is downplaying his ability as a salesman just a little bit, because dealing with probably any instructors, but for sure chemistry instructors, has a certain cat herding aspect to it. And it is very hard to get, everyone's got their own opinions of what to do, and it's hard to get people on the same page. But again, kind of like Norm is saying, originally the courseware had what we thought was kind of complete, like, here's your activities, or lots of activities. Students have lots and lots of interactions during the semester, we've got enough homework. And students who weren't doing all the assigned stuff were asking for more practice. And so it's like, okay, well, fine, and gave them more practice, and sort of targeted, and again, we've provided, like, instructors want activities that they can use, so we're providing them, we can't make them use them, but they're available, and quite a few instructors do.
Yes.
Yeah.
I have one more
Oh,
question,
yeah,
sorry,
sure,
kind of
go ahead.
following up on the question about like how, I know it's impossible to decouple like your effects as an instructor and the effects of the courseware, but do you feel like you were interested in like a flipped classroom? Did you not do a flipped classroom before and this allowed you to do a flipped classroom?
Exactly, yes. So I think I would not have still flipped my classroom if I wasn't aware of the OLI RealChem platform. Because as the resources I was exploring online, videos were not quite sufficient. Building my own videos was not quite sufficient. There was not enough interactivity built in. There was not enough assessment with good feedback built in. RealChem gave me all of that in one basket. And that flipped the switch to flipping the classroom. So I would say maybe it's my effect, but without RealChem, I wouldn't be an effective instructor.
Yeah, like, I feel like framing it
Yeah.
like that is helpful for me to think about it, because when I first look at it, I'm like, oh, it looks just like a Canvas course I could build. But I have to put all that time in to build it, right?
Right.
Like if I'm teaching a course for the first time, or I'm a new instructor.
Right.
Yeah. So
Yeah.
processing it.
Yeah.
Well, and I think the second point on that, making a callback to some of the conversations with panelists. One of the things that happens when we build an individual Canvas course, our individual set of learning resources, is that we don't see what works, we don't see what doesn't work in a larger context, right? We're not sharing the best parts of our innovation, we're not sharing what hasn't worked and killing it. It's an almost anti-Darwinian process.
Mhm.
And so part of the work of OLI, as we think of it, is how do we take this work and make it a collective challenge where we are sharing and innovating and researching together, rather than in sort of smaller isolated pockets. And the structure of the LMS sort of by definition is intended to support your core set of work and innovations, but doesn't have great mechanisms for sharing or validating.
And from the project perspective, if I may add,
Yeah.
we had this community of practice meetings every 2 weeks where the instructors came together from the UC level, from the Cal State level, community colleges, and we had significant discussions about pedagogical approaches using RealChem that worked. And things that work really successfully, Sandra and so on, David, were really open to adopting into the RealChem, making it part of the platform itself. So if it worked for instructor here and there, now it can work for more instructors. So that discussion, that community aspect helped quite a bit as well.
Other questions? Okay, so we have several sort of things packaged in here. We're illustrating like some of our findings. Can't do 3 plus 4 years of work in an hour. So you teach a course, what goes on? Well, pretty simple model here, probably too simplistic, but students start at some point, they go through your course, and you hope they emerge knowing more, being able to do more than they came up, right? And you give them learning opportunities. Oh, I know, this was the other, that I was trying to think of something else. I think I got it now. So I met Dhaval when I was giving a presentation on sort of using a more flipped classroom active learning approach. And I had been doing those for a while before I knew of OLI or before it existed. And I would say the traction was much less initially because there's a big activation energy to take on like a flipped classroom, especially if you're responsible for all the supports. And I think part of what made it work for Dhaval, if I could speak for you a bit, is it's not just like here's an approach, but here's this tool that supports it really well. And you don't have to put in this massive amount of work, to just even get started. So anyhow, you have them learning activities, and then you track student performance. And if you're studying learning, you may do some intervention. And most likely you do a pre-test and a post-test. And then some stuff happens in there that you don't quite know, but they emerge at the other side and you hope it's better. And I think one of the key things about OLI/RealChem is we collect data throughout the whole process. And so I'll show you a couple of things based upon that. Every student interaction is logged, what they answered, when they answered it, did they ask for a hint, did they get it right, did they get it wrong, etc. And so we're collecting data all along the way. This actually allows us to get some measure of the prior knowledge without doing a pretest. And it gets some measure of where they end up in the same way. And I'll just show a couple things that do this. So all the student interactions within the courseware are traced. It's connected to a cognitive model, learning objectives, if you want to call them that, or skills. We happen to call them knowledge components or KCs, trying to keep the acronyms down to a minimum, but KC is one we will refer to here. And then we have a knowledge map. It's a list of the knowledge components and how that courseware activities connect to that. So every question students do, it's logged with, or it's what's the word, not marked with, tagged with a skill or the skills. This is a somewhat random number, but we've been getting, over a million transactions per semester. So like, 300 students gets you close to a million interactions. All right, so anyone know what a learning curve is? Okay, some of you are excluded from answering that. You can probably guess somewhat. So one of the things we get from analyzing data within the courseware are these things called learning curves. There's different ways you can look at them. We're probably going to only look at one way now. I don't think there's going to be time to do the other. If anyone's interested, we can. So we track learning interactions, which we actually call opportunities, versus how students perform. And the measure of performance is the probability the student succeeds on a task, which means they get it correct, but they didn't ask for a hint. And what do you think a learning curve might look like if we track students interact with stuff versus their performance? What does it roughly look like? It goes up. Now, the shape of the line depends upon what you graph. So we do things using a mixed effects logistic regression model. And it's got a growth model and cognitive model graphed into that. The simple thing would be, imagine somebody comes in knowing very little, really low. You don't learn too little to make much progress. And then over time, you start learning more and it kind of ramps up a little bit. And then when you start getting close to everything, then it slows. And I got to be careful about my terminology here. There's what's behind it. And that's probably enough for now, right? Okay, so basically we have a bunch of parameters, initial knowledge for student, overall for the class, and for each knowledge component, and then parameters for learning rate, and all those things get varied, and then you sort of see what gets optimized. And if you do this, which is the way we do, on a log odds scale, so not just, so it's the log of the probability, which is not super easy to wrap your head around exactly what that looks like. But if you do it that way, log odds of a correct response without a hint versus number of times that the student has engaged with a KC, it actually on this scale is pretty linear. Okay, the intercept, if you go back to interaction 0, like before they've ever done the first one, that's essentially the measure of what they know they're coming to the course, right? That's like prior knowledge. And then the slope is your rate of learning. Okay. And even for the algebra challenge, we can probably do the y equals mx plus b growth model. So another question for you. Here is the typical learning curve or an overall learning curve for, let's say, an average median student in your class. What would it look like for a higher performing student? And you got some choices on intercept and slope. Someone who does better in the course, yes. Who gets more things away, earns a better grade. Yeah, no, it's a good question, right? Because there's a lot of ways you can. And I won't put people on the spot if you think you know what it looks like. All right, so here's one of the kickers. This is actually my class and one of my classes from a few years ago. I used this just because I don't have as many students as some of the bigger institutions where it looks really messy. But I was very surprised when I first heard about this, and this is results that Ken Kadinger's group did with 15 different institutions in 8 different disciplines or something. So this happened, this is what occurs in all kinds of courses, not just chemistry, but they're incredibly parallel to each other. Yeah.
Sorry, I can't believe this. This is one of my favorite kinds of scientific discoveries, right? Somebody goes off, prove a thing, and finds out exactly the opposite. And so what this team set out to understand is, we know instinctively that there are fast learners and there are slow learners. What makes for the difference? Like, why do some learners learn faster than others? And what they found is that it's nonsense, right? Like, when you put these students into a similar learning environment with similar opportunities to learn, no one's learning faster than anyone else. They're gaining knowledge at the same rate. They come in at very different places. And I love this both because I love counterintuitive scientific findings, but also because this is actionable, right? Like, as an engineer, I can take this and start to build learning experiences that try to encourage those students to take more opportunities. I can find ways to improve the course, where improve the course means making this steeper. Like, that's genuinely exciting. Sorry about that. I can't shut up.
No, that's, thank you for doing that, because, yeah, I mean, Ken was not, he was trying to find out something different than what he found, yes. And we will get a little to that moral of the story, like what we can tell students, at least in my opinion. Oh, yeah, sorry.
Just remind me, you said that the way you measured that was how they decreased their rate of asking for hints. That's what that's showing us?
So that is just their probability of getting a question correct without asking for a hint, yes. I mean, if you ask for a hint, that's like
Yeah,
getting a boost,
Yeah.
right? So it's like, what's your likelihood of just getting it right?
did they all kind of like, okay, never mind, I'm good.
No, it's,
Like, do they all end up at the same
Ah.
spot? That's what I'm trying to figure out, like, where they
okay,
end.
no, okay, so, yeah, no, excellent.
Number of opportunities, they can, if you give them enough.
Yes,
opportunities.
no, yeah, exactly, exactly. Okay, so first of all, stunning finding, everybody learns at the same rate. If you're doing the rate in terms of number of opportunities taken, that is not how much time you spend, right? Somebody could spend longer per opportunity. Okay, so just to be clear about that, because often we think of rate and we assume maybe it's time. So here's a big mess for way more students than mine, but it still looks the same, right? Okay, and that's Ken's paper on this. Each line is a different student, but they all have relatively similar, astonishingly similar rates of learning. But this person starts not knowing too much coming into the course. And this person, we may not have much to teach. Yeah,
Well,
relative.
I mean, I think, you know, this is. We hear these terms, achievement gaps.
Yep.
And opportunity gaps, and sometimes I think people think opportunity gap is a polite way of referring to an achievement gap, but it's literally an opportunity gap.
Mhm.
But in some ways, then, you know how people feel like narrowing what I'll then generically term equity gap, like people still get flummoxed because, okay, lower performing students are doing better, but then the high performing students are also doing better, so the gap's not narrowing, but is it really because they have roughly the same number and types of opportunities that you're not really
Well,
catching up on the opportunities?
We may get to a few things pertaining to
You got that?
but no, I don't know, go ahead.
Well, no, and I think catching up in this case, remember that there is no individual skill where we're encouraging people to take an infinite number of opportunities, right? There's a point where you gain mastery and you should stop. And so that's what catching up is. Catching up is gaining mastery. The other challenge though, and I suspect you'll talk about this, is how many opportunities do you need to reach mastery and how many are you taking? And how do we structure a learning environment that doesn't place the burden of spending more time and more opportunities on students that already have a job and are taking care of family members, and simply like, that's simply exacerbating the equity challenge. We say, well, it's a problem, you need to spend more time, take more opportunities to learn. Like, we've discovered something amazing, but it simply made an already complicated problem more complicated and tightened the knot. We don't have great answers there.
Well, and just, the fact that students don't have unlimited time,
Mhm.
I mean, it is about scaffolding the right level of opportunity, right? Not just to keep beating your head against the wall.
Correct.
Mhm.
And making, from my perspective, and making each opportunity as valuable as possible, and really shifting the steepness.
Yeah, I would say to me, that's one of the take home messages is if we can increase the efficiency of learning, if we can support the learning better, make every opportunity more valuable. Quick note at the risk of confusing people, those aren't astonishing parallel, right? Okay, that's because, oh wait, I went too far, went too far. There we go. Those are learning rate, the previous graph was learning rate, each line is a student. This one, each learning rate is a different knowledge component or skill. So for everybody, so it's like average over a student. So let me simplify this a little bit, like I just picked 20 or 40 or whatever at random. And recognize physical and chemical properties. They're not learning much, but they kind of already do things, okay? So the Clausius-Clapeyron equation, anything using that and solving stuff, they aren't making much progress. They didn't know much to begin with, and they're not making much progress. So each knowledge component, those are different rates. And one of the things I think what Norm's alluding to is like, maybe we don't spend too much instructional time on physical and chemical, but we probably have to do something about, Clausius-Clapeyron equation or, concentration lines or things we think are important and aren't having the kind of learning rate we want. I don't think we won't get to that today, but part of the thing we do is digging in deeper into these learning curves is then to identify which types of, or where we have good learning, where we don't, and then we target improvement at the not so good learning. So, yeah, sorry.
Am I interpreting it wrong that the negative line would actually mean the more opportunity you have, the less you're actually learning and getting the right
Yeah,
answer?
so maybe, but there's a little nuance here, I think. Number one is that's assuming each question is equivalently difficult. And so we do have this sort of progressive, like we start with things very scaffolded and then they become harder and harder. And so, I mean, you could have a pretty, what looks like a flat learning curve where students are learning because the questions are getting harder and have much scaffolding. Here, yeah.
It sounds like maybe you don't want to teach that.
Yeah, I mean, my gut has always told me that's, even though we spend time on it, students get that pretty quickly and yeah, I would argue, we don't need to spend much time on it. Oh, well, okay. I would like to at least do this one more before we run out of time, just because I think it ties in nicely. And it kind of came from Ken's work. So we have this idea, math's important in chemistry, right? But there's a lot of chemistry that isn't that mathy. And so we looked at several research questions looking at students learning chemistry. Initially, we started with, how much does their preparation matter in terms of learning chemistry and does it slow them? And then we looked at whether, looking at the chemistry problems based upon their math content and how that affected how students learn. And then what's the effect of lower math preparation compared to lower chemistry preparation. Did a study with 4 community colleges at 4 different instructors, almost 200 students from spring 21, replicated it with more students and more instructors. We have about 250 knowledge components or skills in the course, and they're all coded according to how difficult the math was. And this is in the context of like difficulty within Gen Chem. So high difficulty is like logarithms and a little bit of complicated algebra. It's not really hard math, but it's hard within the course. And I'm going to skip that. We just had to add a couple parameters for math into the model. And I'll sort of just cut to the chase on this. Here's what we find. Maybe take a little bit of time to look at it. So blue is no math involved at all. Green is high math. And probably not super surprising, right? Okay, low math, they started better and they increased. The harder the math was, the less success they had initially, the lower the performance was initially. But, and same thing we talked about before, where we get kind of a pretest on their knowledge. If anything, the learning rate for the hard math, quote unquote hard math, is slightly higher. It's not really that significant in both studies. It's kind of close. But we think, so I don't know how many of you have, like, when I started teaching, students were required to pass an algebra class before they could take chemistry, and that was a big roadblock for some of them. We would argue that, or we would posit that this argues for maybe you don't need a remedial math course ahead of time. You can learn the math in place, and we're not even really supporting math instruction. We're just like showing them how to do it. We're not doing some of the like, oh, here's the sum of quadratic or something like that. So I think we could even improve that. And then there's a couple other things that are, I think, a little bit interesting. I don't know what you would guess in terms of the effect of their math preparation or their chemistry preparation, if we think of those as separate things. I would have said my students who are good in math were also good in chemistry, or knew that coming in. And then sometimes I've had like, oh no, nope, that's not the case at all. So if we, each dot's a student, if we graph math initial knowledge that we get from our analysis versus chemistry initial knowledge, they're not really correlated at all. And some of you were guessing that, it sounds like. This is possibly surprising though. Their chemistry initial knowledge is associated with overall learning, but their math initial knowledge really doesn't have that much of an effect, which I think supports that notion as well. Oh, and I think, yeah, so this is like, maybe this is an argument, we don't need math remediation. And there's all kinds of different measures we have of like how many opportunities you need to quote unquote catch up or to reach a certain level. But here is one measure that came from this study. The less typical less prepared student, like the lower 50%, the first quartile, starts a little less than 60%, takes about 17 opportunities to get to 80%, and on average they do less than half of that. If you're in the like third quartile, you'll be starting at 70%, maybe it takes you 5 opportunities to get there. Okay, so we're not solving the problem of you need more time, probably, right? But I think it's a good lesson to students that's like, no, you are not learning at a slower rate. You may come in with less initial knowledge, but if you put in the time, you can get there. And I think we're just about out of time, but I'll do the like super quick thing with just one other result. This is from Josh Hartman at UCR, who did, he used mastery learning along with OLI at the time, which is now real chem, and essentially had students repeat taking each unit, quiz, whatever you want to call it. And that was worth a huge chunk of their grade, and then that could replace their final exam and midterm, but it could replace lower performance. But the main thing was they could replace a lower performance in any of the first attempts at the unit with the subsequent attempt. And it was broken down in a number of different ways. I'll just show you really quick ethnicity. So there was one teacher who taught traditionally, a second teacher who added mastery learning, and then Josh did mastery and OLI. Yes, they're different instructors, so there's probably an instructor effect, et cetera. And consistently, the not URM students had higher performance, but I think you can see there's a pretty big bump in a closing of that gap for the students who use OLI as well as mastery. Same thing with first gen, and it's a much, much bigger effect. Might be worth noting that final performance here with mastery is more or less what the control group had. So that's a pretty nice argument for that, helping somewhat to close that gap, and the gap closed quite a bit here. And then probably last thing on this, since we're out of time, we then dug into how the students were interacting with courseware. I'll only show you the first gen stuff here. And this maybe be just a little bit quick, but the red line is the first gen students, number of interactions they had with the courseware versus their final exam grade. And this was a common final exam for all of the instructors. And the continuing gen students, how much they interact with the courseware, kind of not much of an effect. But the continuing gen, or sorry, the first gen students, if you do enough, you can actually surpass the continuing gen students, at least that's the moral of this. And then we looked into like, does that correlate with how many transactions they did in the actual unit for that particular mastery, and nice correlation. And let's see, was this one? Oh, and then, yeah, if you do a second mastery attempt, it bumps up. They didn't do quite it, not as many people did the third mastery attempt, but it's like every engagement with the courseware helps. And I think maybe close with, we have a number of measures of this, but probably the one I think stands out to me is the average high engaging student who does maybe like 900 interactions in a transactions within a semester, compared to somebody who's very low on engagement. It's about a letter grade increase, and that seems to be in how you do on final exam type of stuff as well. Okay, and we probably should just jump to our thank you slide and see if there's any other questions. I think we're at time, if not more. Okay, get it. Oh, no, gotta do that. Thank you. We mentioned this already, but I think this is a key point now that we have a little picture with it. We think that OLI/RealChem can be a sort of research lab for science education, sort of like a particle accelerator for physicists or a high energy collider. We have this infrastructure that helps with setting up learning studies, changing instruction to help students learn, et cetera. Norm may want to weigh in more on that. And we collect tons of data, and we do want to thank all of our funders, of course, starting with the fabulous Learning Lab for helping us get started and helping us to get the big grant to continue this work for real.
And that notion of a particle accelerator for discipline-based educational research. One of the key elements to this was bringing together so many different kinds of faculty, so many different kinds of students from so many different populations. And so this is, I hope, one of the success stories for Learning Lab about needing to bring together an intersegmental group that really is representative of the larger cross-section of learners who want to support, but without that larger cross-section, this research becomes much narrower, much less interesting, and much less actionable. So this is one of our success stories, but we hope it's one of yours. Like this is really important.
Yeah. And I was asked or reminded to let folks know that if you could evaluate the session on WOBA app.
If you could give us some session feedback and leave the app, give us some data to help us iteratively improve. You can either go to surveys and find the session, or you can go to schedule and hit the session and find session feedback. If you don't have to go, we have a few hard copies, but this makes our lives easier if you use that, and it enters you into a faculty.
And we have a table, and you're welcome to stop there. And Dhaval and I, and probably Norm and Joe, are around and happy to talk to anybody in more depth and show you stuff. And we're always looking for more people who want to.
If I may throw in a final anecdote, tomorrow I'm getting lunch with 3 students who are currently at UCLA, transferred from Mount. They asked me why I'm visiting, and I said to present on RealChem. Oh, I'm taking organic chem. Is there a RealChem version? Just an anecdote, but yeah, that was the first thing that they texted back.
Yeah, thanks, everybody, and happy to chat with whomever, and got contact information if anybody is a chemistry person and wants to give it a try, and so on.